The project may be finished, but is the engineering learning finished?
Before we begin, let me briefly explain why I am sharing this story. I started this journey as an engineering student, working on projects and trying to turn what I learned in the classroom into something that actually worked. After graduating, I continued my engineering development through practical training under the supervision and mentorship of Professor Kapila Jayasinghe. Looking back, I can now see something that I did not fully understand as a student. Building a successful project is important, but making it work is only one part of learning to become an engineer. In this presentation, I would like to share that experience from the perspective of both an engineering student and a young graduate engineer. When I was a student working on engineering projects, the immediate goal was usually very simple: make the project work. We would spend weeks designing, finding components, building, programming, and solving one problem after another. Then, finally, the robot would perform the task we wanted. We could demonstrate it successfully, and naturally, we felt that the project was complete. But looking back now, I realize that this is exactly where we should have asked another question. The project works, but have we completed the engineering learning? Or have we only reached the point where some of the most important learning can begin? An engineering project is not just about building a robot or a device. It gives us an opportunity to apply what we have learned, solve practical problems, make engineering decisions, and develop skills that cannot be learned from textbooks alone. We also learn how to work with others, to communicate, plan, divide responsibilities, and bring different parts of a system together. So projects are extremely valuable learning experiences. But building the project is only part of that experience. Once we test what we have built, we begin to discover what worked, what did not work, and what we did not fully understand. And that is where another important stage of engineering learning should begin. This is what I now understand as the missing learning loop. Building and demonstrating the project are important, but they should not be the end. Once the system works, we should test it properly, under different conditions. Then we need to analyze the results and ask why it behaved the way it did. What worked? What did not work? Which assumptions were wrong? What do we now understand that we did not understand when we started? That analysis should take us back to learning, sometimes even back to the theory. Then we redesign, improve the system, and test it again. So the real engineering learning loop is not simply build and demonstrate. It is build, test, analyze, learn, redesign, and test again. And unfortunately, this is the part of the loop that many student projects do not get the opportunity to complete. During an engineering degree, we follow an approved curriculum, and projects are an important part of that learning. But many of these projects have to be completed within a single semester. At the beginning, we need time to understand the problem, develop the concept, and plan the project. Then we have to design, find the components, build, program, integrate, debug, and finally demonstrate the system. By the time the prototype is actually working, the semester is almost over. And this creates an important problem. The working prototype has now given us something extremely valuable, real results that we can analyze. We can begin asking what worked, what did not work, why the actual performance was different from what we expected, and what should be redesigned. But often, just when we reach that point, the assessment is completed and the semester ends. So the project may be complete according to the academic timetable, while the engineering learning loop is still incomplete. There's another way many of us begin learning engineering, outside the formal curriculum. Some students become interested in robotics, electronics, or embedded systems and start learning by themselves. We watch videos, read tutorials and documentation, find example programs, buy components, and begin building. Robot competitions can provide a very strong motivation for this. They encourage us to learn quickly, work as a team, solve practical problems, and somehow get the robot working before the competition. I believe this kind of initiative is extremely valuable. It can teach us things that are very difficult to learn only from lectures. But there is also a limitation. During the competition, our immediate objective naturally becomes make the robot work, solve the problem, and compete. Once the competition is over, the team may move on and the project may stop. So once again, we have learned a great deal, but we may still not have completed the engineering learning loop. Let us look at a simple example from student robotics projects. Suppose we build a robotic arm using inexpensive RC servos, and the robot successfully performs a pick-and-place operation. It moves, it follows the programmed path, it completes the task. So can we say the engineering design has been validated? Not yet. There is nothing wrong with using an RC servo for a prototype. It may be an excellent choice for learning, developing the mechanism, testing our software, or demonstrating the basic concept. But we need to be very clear about what that prototype has actually validated. Can the servo provide the required torque with the real payload? Is it fast enough? Is the positioning accuracy sufficient? What about backlash and repeatability? Can it operate continuously without overheating or failing? These are engineering requirements, and simply seeing the robot move does not answer them. So the lesson is not don't use RC servos. The lesson is understand why you are using them and what you are trying to validate. A prototype can work successfully and still reveal that a different component will be required for the final engineering solution. That is exactly what a prototype is supposed to teach us. By this point, we can see that there are several reasons why the learning loop may break. 3 of the most important are time, guidance, and funding. First, time. In a semester project, the assessment arrives and the semester ends. In a competition project, the competition date becomes the deadline. There may simply be no time left for deeper analysis and another development cycle. Second, guidance. When we are still learning, we may not know what measurements to take, what questions to ask, or how to interpret what went wrong. Without experienced supervision, it is easy to stop once the system is working. And third, funding. Testing version 1 may tell us that we actually need a better motor, an encoder, a different sensor, a stronger mechanical component, or proper test equipment. But students may simply not have the money to purchase those components and build version 2. So when a project stops here, it does not necessarily mean that the students are not interested in learning more. Very often, there are practical reasons why they cannot continue. The important question is, does the engineering learning also have to stop? Suppose our testing shows that version 1 needs a better motor, an encoder, improved sensors, or some other expensive component. What happens if we simply cannot afford to build version 2? This is something I think we need to understand clearly. The physical project may have to stop, but the engineering learning does not have to stop. We already have something very valuable, version 1. We can measure its performance and use the data we have collected. We can analyze problems such as insufficient torque, positioning error, vibration, overshoot, or overheating. Then we can go back to engineering calculations. We can calculate the torque that was actually required, determine the necessary speed and accuracy, specify a suitable motor and gearbox, reconsider the control system, and redesign the mechanism. We can even estimate or simulate how the redesigned system should perform. We may not have the money to purchase those components today, but we can still explain what was wrong with version 1, what version 2 should contain, why we selected those components, and what improvement we expect. That is already a major step forward in engineering learning. So lack of funding may stop us from building version 2, but it should not automatically stop us from engineering version 2. This brings us to what I think is one of the most important ideas in this discussion. Even if we cannot physically build version 2, we can still complete what we might call the intellectual learning loop. We begin with version 1 and measure its actual performance. Then we analyze those measurements. What worked? What did not work? And most importantly, why? Next, we calculate. We use the engineering theory, equations, and models we have learned to understand what the system actually requires. From that, we can specify version 2. What torque do we really need? What speed, accuracy, stiffness, sensor resolution, or control performance should the next design achieve? Then we redesign the system based on those requirements, not simply by trial and error. And finally, we predict. Based on our calculations, models, or simulations, how should version 2 perform? At this point, we may still not have purchased a single new component, but something very important has changed. We now understand version 1. We know why we would change it, what version 2 should be, and what improvement we expect. That is engineering learning. Building can wait until resources become available. Engineering thinking does not have to. Before we leave any engineering project, I think there is one question we should always ask. What did version 1 teach us? Not simply, did it work? What did we actually learn from building and testing it? Which of our original assumptions were correct and which were wrong? What happened that we did not expect? Did we select the correct motor? Was the structure stiff enough? Were our sensors accurate enough? Did the control system behave as we expected? What calculations should we have done before we built it? And if we were given the opportunity to build version 2, what exactly would we change and why? If we can answer these questions using measurements, engineering theory, calculations, and evidence, then version 1 has done something much more valuable than simply completing a task. It has taught us how to make the next engineering decision better. So perhaps the most important output of version 1 is not the prototype itself. It is what version 1 teaches the engineer who built it. So, if there is one idea I would like to leave with you from this discussion, it is this. Do not let your engineering project end at "it works." Build it, test it, measure what actually happens, analyze the results, go back to the theory and learn from what you observe. Then, redesign. And when possible, build again and test again. Sometimes the semester will end. Sometimes the competition will be over. Sometimes we may not have the money to build version 2. The physical project may have to stop, but the engineering learning does not have to stop with it. Looking back at my own journey, from being an engineering student to continuing my development as a graduate engineer under supervision, I now understand that becoming an engineer is not simply about completing more projects. It is about learning more deeply from every project we complete. Build, test, analyze, learn, redesign, test again. Because sometimes the moment a student project ends is exactly the moment the real engineering learning can begin.